So, this module is going to be about the method of moments, which is the name given to the way in which we solve the integral equations. So far we have seen one simple example of integral equations, which is the volume the wire with the charge, surface charge on it, and we wanted to find out the electrostatic potential. The second thing that we formulated was the surface integral equation, and we want to find out now how do we solve this. Okay, so roughly the layout that we will follow, this is going to be a slightly lengthy module, is before we get to the method of moments, we will look at some math, motivation and generalization of the idea, mathematically what it is, and then we will apply it to two, these are applications. So, you learn the general theory and then we apply it to two problems. So, that is going to be the approach, and we will now, when we do this, we will have to apply everything that we have learned so far. So, starting with integral equations, Green's functions, numerical techniques of integration, everything comes together in this module. Alright, so let us go ahead. So, let us look at the motivation over here. So, let us go back to the very original problem that we started with for motivating integral equations themselves, right. So, everyone remembers this integral equation, right. So, we had a wire along the y direction, right, that is what it was, and we wanted to find out the potential at any point in space over here. That was what the problem was, right. And further, what was given was that this cylinder was connected to a constant voltage, right. So, everything was at a constant voltage, and that is how we had set the problem up, and in solving it we had two steps, right. So, first of all, in this problem what was unknown? The charge distribution rho, right. So, rho was the unknown, and so the first step was to find rho, and to find rho what did we do? First step was we discretized the line segment, and then we expressed it as in a basis, right, in terms of a basis function, and we used a simple pulse basis function, right. Once we knew this, then we knew everything inside the integrand, and I could evaluate this and find out V anywhere, right. That was the general approach that we did. So, looking at this formulation that we did so far, right. So, for example, if I wanted to take one equation, so remember this gave us a n cross n system of equations which we used to solve for rho. So, let us look at just one of those equations. So, let us take one of those equations that corresponded to, let us say, the mth segment and the midpoint of it, right. So, this was, let us say, some R m. So, what did this equation read as? The mth equation in these n cross n. So, the left hand side would be, right. So, yeah, so there is a 4 pi epsilon, we can keep it on the right hand side. So, there is V of R m, right, that is the point where I am enforcing my known condition, is equal to 1 by 4 pi epsilon, and there is going to be a summation over small n is equal to 1 to m, capital N, sorry, and so there is going to be a bunch of things over here, right, and the pulse basis function, if I call them as B n, right, B n of, let us call it r prime, right, it is going to be some integral over a d r prime. That is how we did it. Whatever is inside does not matter. And in this equation, the way we solved it is that the left hand side, this V of R m, we know it to be fixed at 1 volt. That was given, right. So, what we ended up finding out were the coefficients of these basis functions, right. So, that allowed us to express rho. So, this is just a review or a summary of what we have already done and seen so far. So, now having seen this, now that you have refreshed your memory about it, if I ask you what would be some of the problems with this approach in terms of accuracy, what do you think? The accuracy depended on the number of cells, right. The larger the number of cells, the better was the solution accuracy, right. So, of course, that is an approach, need a large number of n, and we saw that in the graphical results also. even if I fix a large number of n, is there any other problem conceptually that you can see? Basis, yeah. So basis functions may be unrealistic, like using a pulse basis function may be unrealistic, but using a triangular basis function may be better, right? So basis functions can be better. Anything else? So let's say that I have got very good basis function, I have chosen a large value of n. Anything else that could be a problem over here? So the hint is the left hand side. What is known, or rather what is given to you in the problem? Where is the voltage given? Surface, right? The surface of the cylinder, this metallic perfect electric conductor is given to be this thing. So every point on this cylinder has constant voltage. Where all are we enforcing this? We are along the center, but at discrete points. At how many discrete points? N discrete points. By doing this, are we doing anything to ensure that the voltage between Rm and Rm plus 1 is still 1 volt? We are enforcing the left hand side at Rm, then the next, so we have one segment over here, we have one more segment over here. So first equation will take this point, second equation will take this point, and so on. But we are doing nothing, we are just hoping that the solution turns out to be smooth and well behaved and all of that. But we are not doing anything to ensure that the solution is continuously 1 volt everywhere, right?
1 volt at the cell, right?
Yeah. 1 volt, no, the voltage that is given is at every point on the wire.
But we are increasing n.
As we increase n, we are approaching that. So my question is that keeping n fixed, choosing good basis functions, still is there something better that you could do? Right? So the answer is yes, and that is what the method of moments tries to do. So what we did over here was essentially we discretized the integral equation and solved it, right? So the main problem with this approach is that we are not enforcing V of r is equal to V naught at points other than Rn. Okay. Right. So the more robust method is what is called the method of moments. And this method of moments is actually, it's a very general term. It includes integral equation methods. It also includes finite element methods. Okay, so it's found throughout engineering.